Hello everyone, my name is Fred Rispoli and I'm coming to you from Stony Brook University. In this video, we're going to cover some key examples from Chapter 1 of On's book, Probability and Statistics for Science and Engineering with examples in R. In particular, we'll look at three examples. The first one will discuss frequency distributions and histograms. The second example will be focused on calculating standard deviation, and the third example will be based on calculating a 5-number summary and box plots. Now, these examples were chosen based on some frequently asked questions by students and by my observations of where students struggle on exams. Okay, so in this first example, we're going to go over exercise 1 from On's textbook. So we're given ages of 62 people who live in a certain neighborhood. A little bit long of the data set, but it's still manageable. And we're asked to display the data in a frequency table. And I add to this, use classes from 0 to 9, the first class, 10 to 19 would be the second class, 20 to 29 the third class, etc. And let's say you're asked to display the frequencies as well as the relative frequencies. Once we have a frequency distribution, we'll be interested in displaying the data in a histogram. Once we could visualize the data, then in part C, we asked to describe the shape of the distribution. And finally, in part D, you're asked to display the data using a stem and leaf plot. Okay, so we can put together our intervals, as I said. The first one, 0 to 9, the second, 10 to 19, the third, 20 to 29, and so forth. Okay, so these are these class intervals. Sometimes you may be given the intervals. Other times you want to try to take the range of your data and divide it up into equal intervals. The number of intervals is generally somewhere between 5 and 15. Remember, you're trying to summarize the data. So here we have 62 data points, and we're going to use these 10 different intervals. Okay. So the next step would be to go through the data set and count the number of values in each interval. So let's try to do that for this first interval. We have 0 to 9. So if we go back, okay, you can see that this list is given in order, okay? So we could quickly see that there are 3 values between 0 and 9. And so that's where this frequency 3 comes from. Okay, let's do that again. Suppose we wanted to count the number of values in the interval 10 to 19. Well, again, this ordered list helps. So we get 1, 2, 3, 4, 5, 6, 7, 8. And I believe there's 9. 2, 4, 6, 7. Take that back. So we have 7 values in the interval from 10 to 19. So we would continue along counting the number of values in each interval. A nice check is to add up the frequencies and see that, this sum is 62. Go back to your set, check the number of values in your set. We could see we had 62 values there. So that's one check just to make sure you've captured all the data. Now, the relative frequency is what we get when we take the frequency and we just divide it by the total sample size. In this case, it's 62. So here, as a fraction, the relative frequency is 3 over 62. but we could express this as a decimal, 0.048, and even convert this to a percent if we wanted. So we get 4.8% in this class interval. And then as a second check, we may check to see that these frequencies add up to 1. Occasionally, there might be some round off error. In this case, I believe if we were to add all of these, it adds up to 0.999, but if we round that off, we would get 1 as well. Okay, so this is our frequency distribution. Now, using the frequency distribution, we can create a histogram. Okay. But the idea with the histogram is we try to list the intervals, but we might express these classes so that you get one continuous line down here on the horizontal axis. So here we would be going from 0 to 10, let's say, and then from 10 to 20, and so on. And then we create bars, okay, that represent the frequencies. So we know that our frequency for this first class interval was 3, so the height of this first bar should be a 3. Okay. In the second class, we had a frequency of 7, so the height of this bar should correspond to 7. You could see that's close, maybe slightly off, but that should be a 7. By the way, this is a histogram that you could get using R. So we would continue going through this. Notice that we have the interval from 40 to 49 has the highest frequency by far. You could see over here we have 15, and over here we get a height of about 15 over here as well. Okay, so that's how we get our histogram. We do it as a two-step process. We create a frequency distribution first, and then we have a histogram. Okay, when we look at this, we may say that the shape of the distribution is bimodal. I have sort of a modal class here and a second modal class here. So that's why we could say that it's bimodal. And there's a slight skew to the right. You could see this sort of thins out. So we may say that this is skewed to the right. The last part of this problem is to create a stem and leaf plot. So here we will use the tens digit as our stem and then the other values as our leaves. So we had the numbers from 0 to 9, they were 2, 5, and 6, so they show up here. Then in the next interval, remember if we go over here, 10 to 19, these values were 12, 14, 15 twice, 16, 18, and 19. So in the stem and leaf plots, you could see we have a 2, 4, 5, 5, 6, 8, 9. Okay. Notice how you could recover the original data from the stem and leaf plot. Right, this corresponds to a 12, the 14, a 15. If we go to the next line here, I see I had a 20, a 22, a 23, 25, 27, and 28. So this is our stem and leaf plot, where we have the tens digits as stems, and the ones digits would be the leaves in this plot. Okay, let's move on to example 2. So example 2 is about calculating standard deviation. Okay, let's say we have a data set that looks like this. We have the values 6, 12, 2 more 6s, 4, and 8. and we want to find the sample variance and sample standard deviation S two different ways. Okay. The first way is what I will call using the definition formula for sample variance. Okay, in the definition for sample variance, we look at our data values minus the sample mean. We square that, right? These values here in parentheses are sometimes called the deviations, and then we look at the deviations squared. So we should result in, these should all be either 0 or positive. We sum that up and then divide by n minus 1. Okay, so that's our definition. It gives us sample variance. And if we want the standard deviation, we would take the square root of this. Okay, well, there's also what I will call a shortcut formula, which tells us that, well, we could look at the sum of the data points squared minus the sum of all the data points, and then we square that sum, divide that by n, and then we simplify this numerator and divide by n minus 1. So if you have 5 or 6 values, you'll see it's about the same amount of time. But once you go over that, 10 values or so, the shortcut formula is quicker, okay, and is useful for a few things we'll study later on. So it is very much worth understanding how to use this formula. Okay, so using the definition formula. So here we have a first step. We have to find the sample mean. Okay, well, it's fairly easy to see that the sample mean is 7. If we were to add up this column, right, this column adds up to, let's have 18, 24, 30, 34, 42. We have 42. We divide that by 6, and that will give us a sample mean of 7. Okay. Then we look at deviations. So the deviations are obtained by subtracting 7 from each data point. So 6 minus 7, negative 1. 12 minus 7 is 5. Negative 1 again and again. And you can see what happens here. This should be a positive 1. And then our next step is to square the deviations. Okay, so all of these should end up being positive, and we add this up, we'll get a 38. To finish this, we find the sample variance by taking 38 and divide by 5. Right, I have 6 data points, so n is 6, but we divide by n minus 1, which is 5. We get 7.6 for the sample variance. And the sample standard deviation is the square root of 7.6. So I would get 2.76. Okay, now we could also do this using the shortcut formula. So if we think of our list of observations, we refer to them as the xi's. You could see that if we add up that column, we get 42. As noted before. And now we don't need to calculate a sample mean and subtract, okay? We simply need to find the xi squares. So we go down this list, 6 squared is 36, 12 squared 144, and so on. 4 squared is 16, okay? We'll need the sum of this column. So if we add it up, we get 332. Now we'll use our shortcut formula. So this says to find the sum of all the x squareds. Okay, so that's my 332. So that's our first term in the numerator. And also in the numerator, I have this fraction where we take the sum of all the x's, 42 in this case, and I have to square that sum, and we divide that 42 squared by 6. Okay, and once again, in the denominator, we're dividing by 6 minus 1, which is 5. So we could work this out, and you'll see you get 7.6, once again, which matches our result that we had in Part A. And the standard deviation is the square root of 7.6, which is 2.76. Okay, of course, there are other ways to find standard deviation in this class. One way would be to use R, okay, the programming language R. And I've created a separate video for that. So if you want to learn how to find standard deviations using R, you may want to look through that video. You may have a calculator that could find standard deviations. Also, you could use Excel to find a standard deviation. Now, you can't use all of these when taking a test, but you could certainly use these when you're working on a homework problem, or it's also a good idea to check your calculations using some sort of technology, whether it's R, Excel, or a statistical calculator. All right, let me spend a minute or two just talking about why variation is so important in a manufacturing process. So imagine you're creating a certain part, okay? Perhaps a part for a motor is a good thing to think about. And you know that down the line, this part needs to fit together with other parts, right? For example, a cylinder in a car motor needs to fit inside a car engine, okay? So you may have engineering specification limits. So imagine that these blue lines are spec limits. This is what we might call the upper spec limit and the lower spec limit. And you're producing parts, and you take measurements. Let's say you're measuring the diameter of the cylinder, and you would have many of these. You're producing, hundreds, maybe thousands at a time. So you have enough where you could create a frequency distribution and then a histogram. Okay. Well, when you create the histogram, if you imagine its general shape, you could think of it in terms of sort of a curve. Okay. Now, when you have a wide variation, let's think of this curve over here as sort of the output of a process with a wide variation. You could see that this area in here would represent defects, okay, both over here and over here, okay? And so that leads to sort of a waste of time and money. And what the engineers would like to do is to improve the process so that your output looks more like over here. Okay, so that's all a matter of reducing the variation. So people would use standard deviation or the variance to measure this, try to make improvements, and hope that after the improvements are made that their output looks more like this curve here. And now all the output is within the spec limits. So monitoring variation in standard deviation becomes a very important piece of quality control. Okay, and calculating, the average does as well. You want to make sure that your process is well centered. Even if you have a small standard deviation, if your center of the output is over here, you'll still be producing defects. So maintaining statistics on the process average and the process standard deviation is vital in many manufacturing processes. Okay, here's what I call a stop the video exercise. Suppose you have this data set. These are ages of students. We have a data set 9, 8, 12, 5, 3, 6, 13. And I'm going to ask you to find the sample standard deviation three ways. The first way is to use the definition formula. Okay, so that's the formula that you'll see in many books, and that is the formula that looks like, let me find it for you, the formula that looks like, let's see, where did it go? Right here. Okay, here is our definition formula for standard deviation. So we'll calculate the standard deviation using this the first time. And then part B is to find the standard deviation using the shortcut formula. Okay, so I would suggest stopping the video and practicing these two different ways of finding a standard deviation. And then if you are familiar with R, or if not, hopefully you'll watch the video basic data analysis using R, so you can also confirm the answer that you're getting. Okay, as a quick answer, our final answer should be 3.65. All right, let's now turn our attention to example 3, calculating the 5-number summary and box plots. So suppose we have a data set, and you could see over here we have these values. Let's see, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I have 11 values. We'd like to find the 5-number summary for the data set. We'd like to determine if there are outliers and create a box plot. Okay, so as a first step, we would order the data, right? Whenever you're finding a 5-number summary, it helps to order the data, so you could see that we have our smallest value is 45, then there's a 47, and so on. So we put our data in order. Now, for the 5-number summary, we need to identify the minimum value, Q1, which is the first quartile, the median, Q3, the third quartile, and the maximum. And remember, Q1 is the same as the 25th percentile, and Q3 is the 75th percentile. Okay, so let's review how to find a percentile before we find Q1, the median, and Q3. When we want to calculate, let's say, the pth percentile, okay, step 1 is to order the n observations from smallest to largest. Step 2 is to calculate n times p, and this is where p is expressed as a decimal. So if I wanted the 25th percentile, I would express p as 0.25. Now, two things could happen when you find n times p. It's either not going to be an integer, right? It won't be a whole number, or it will be a whole number. But case 3 addresses the situation when it's not an integer, then we round it up to the next integer and find the corresponding ordered value. So if n times p, let's say, were to be 3.5, we'd round it up to 4, and then use the 4th data point in the ordered set, which you may see denoted by x sub 4. The 4 is in parentheses to denote that the numbers sort of get reordered once you put them in order. Okay, if n times p is an integer, let's say you get a whole number, then you need to calculate the average of the kth item and the k plus first item. Okay, and again, these are coming from our ordered list. Okay, so an example of this is when you're finding a median when you have an even number of values in the list. You find the average of the two numbers that are sort of in the middle. Well, this is exactly a generalization of that process. All right, so back to our data set. So we know we had 11 values. If I want to find the first quartile, I take 11 times 0.25. It gives us 2.75. That gets rounded up to 3. So I use the third item in the ordered list, which is 53. The third quartile, okay, now P would be 0.75. So I take 11 times 0.75, gives us 8.25. We round that up to 9. So the ninth item in the list is 78. Okay. We'd identified the min is 45. The median is easy to find because I have a list with 11 values. So the median would just be the one in the middle or the sixth item in the list. And the max is equal to 99. So my 5-number summary would be 53. Whoops, no, let's start with the minimum. Be 45, 53, 59, 78, and 99. Okay. Now, it's probably easiest to just skip a little bit to part C. Using the 5-number summary, we create a box plot. Okay, so this is roughly what the box plot should look like. This corresponds to my minimum 45. Then this left edge of the box would be Q1, which would be 53. The middle should be 59. I know it looks more like 60 here, but this would be 59. And then Q3 over here would be 78. And then the maximum is 99. Okay, so that's how we create a box plot. So when you have the box plot, it sort of illustrates the 5-number summary. You have the minimum, Q1, the median, not the mean. The median is over here. This is Q3, and then you have the maximum. Okay. Sometimes these quartiles are used to identify cutoff values for outliers. So the idea is to find something called the interquartile range. The interquartile range is Q3 minus Q1. So here we would get 78 minus 53. Okay, so that gives us 25, right? So the IQR is 25. Now the lower cutoff value for an outlier is Q1 minus 1.5 times the IQR. So that would be 53 minus 1.5 times 25, right? 25 is this IQR. So when we simplify this, I get 15.5. So this would be my cutoff value for outliers on the low end, but we also need a cutoff value for outliers on the high end. So for this, we take Q3 plus 1.5 times the IQR. So I have 78 plus 1.5 times 25. Simplify that, we get 115.5. And then I go back and I think, do I have any values below 15.5? Well, the answer to that is no, right? The minimum is 45. Do I have any values that are greater than 115.5? Again, the answer to that is no. I know my maximum is 99. So there are no outliers for this data set. Okay, here's a stop the video exercise. Now in the previous data set there were 11 values, but suppose there's 12. You'd be surprised how much this changes things. Okay, so I'm going to ask you to find the 5-number summary for this list. Let's say I have 2, 4, 6, 8, 10, 12 values in our list. Okay, you could see that this list is not in order, and I believe the new value that was added is 90. So give this a shot. Again, some different things happen when you're calculating the quartiles. Okay, here's the solution. So the ordered data set looks like what you see here. We have 45, 47, etc. The min and the max are easy, 45, 99. Now to find the median, before we had just the middle value, okay, but now I have 12 data values. So the median is the average of 60 and 69, the two in the middle. Okay, so that gives us 64.5. When calculating Q1, if we look at 12 times 0.25, well, that comes out to be a whole number. So when I have a whole number, we have to take the average of the 4th and the 5th item in the list. So I go 1, 2, 3, 4. There's my 4th, and here's my 5th. So I need to take an average of 57 and 59, which is 2. So my Q1 is now 2. For the third quartile, Q3, now my n times p is 12 times 0.75. Again, I get a whole number. This works out to be 9. I need to take the average of the 9th and 10th item in the list. So the 9th and 10th item in the list, 78 is the 9th, 88 is the 10th. We average these, we get 83. So that's my third quartile. So now we could say that the 5-number summary is 45, 58, 64.5, 83, and 99. Okay, that's it for Chapter 1 examples. Thank you for watching.